Hello, I want to share with you this Mathematica notebook that will plot three-dimensional surfaces. It's really cool, and you can get it free for your own computer. And I'll talk at the end about how you can do that. So yesterday, I talked about computing the surface area of the surface you get if you rotate y equals x cubed about the x-axis. And here's a picture of y equals x cubed. And here's a picture of what you get when you rotate it about the x-axis. I used a parametric plot. X is x, y is f of x cos theta, and z is f of x sine theta. And I let x go from 0 to 1, and what theta goes from 0 to 2 pi. That sweeps out the circle. Let's turn it this way. So if I made one of these things and I put it on the ground, it'd be like that. And you would really hurt your foot if you stepped on that. In fact, that is so thin, it's just like remarkably thin. So I want to talk a little bit about how thin that point is. All right, so if x is measured in meters, so this is 2 meters across and 1 meter tall, then think about how wide that point is just a millimeter down from the top. So a millimeter is 10 to the minus 3 meters, thousandth of a meter. So if I take x cubed, I get 10 to the minus 3 cubed, or 10 to the minus 9, and the diameter is twice that. So the diameter, a millimeter down, and you can see a millimeter quite easily, is 2 nanometers. And I mean, nanotechnology and all that is all the rage. And a single gold atom is about a third of a nanometer, according to Wikipedia. So that's really thin. So that you stepped on that, it would go like right between your cells. It would be devastating. But anyway, so let's do another example. This is actually a famous example from some Renaissance dudes came up with this. So suppose you're going to take the function y is g of x is 1 over x. And here's a graph. And I'm thinking about x kind of big. Here, x goes from 1 to 10. And actually, we're going to think about what happens as it goes from 1 to infinity. But let's spin this graph around the x-axis with x going from 1 to 10. Now I get this trumpet-looking shape, or horn. It's been called Gabriel's horn. There's some tradition that Archangel Gabriel will blow the horn at the judgment day. So anyway, so you might want to think about what happens as instead of you have 10, you have 100, 1,000, billion. Let's just make it 20 to see a little bit more of what it looks like. It gets pretty thin. Okay. All right. So let's think about what the surface area of this horn is, or this trumpet. Well, I integrate, and here I'm going to think about the area. If I go from x equals 1 up to x equals b, and think about b being a variable. So the area as a function of b is integral from 1 to b of 2 pi y times square root of 1 plus dy dx squared. We can figure out dy dx minus x minus 2. I square it and I get that. And can I put the x on the bottom? Well, that's a really hard integral to do. I don't know how to do that, but actually Mathematica does. If I have it do that integral, it gives me an antiderivative. Wow. And look at that. It involves the inverse of the hyperbolic tangent that I talked about yesterday. Remember that hyperbolic tangent is a really cool function. It goes from -1 up to 1. But anyway, but it's kind of funny. I did this and I put in the definite integral from 1 to b, and it just choked. It could not give me an answer. And I think it's because it's thinking about the possibility that b is a complex number. But anyway, let's not worry about trying to evaluate that really hard integral, but let's think about comparing that, because 1 plus a positive thing, if I take the square root, is bigger than 1. So I can replace that square root of 1 plus positive by 1. Now this integral diverges, we know. But we can think of it this way. The area of any b is bigger than 2 pi times log of b, natural log of b. Actually, Mathematica will do that integral. It it considers the possibility that B is a complex number. The real part of B is positive, or B is not a real number, is what it's saying here. But let's not worry about that too much, because we know we can take the limit as B goes to infinity of 2 pi log B. That's infinity. And I can make log B as big as I want by making B big enough. So the surface area of Gabriel's horn is infinite by the comparison theorem. Wow. So, but we can compute the volume that's enclosed in this horn, especially like if I take it and I move it like this, put it up, move it up, and then I kind of pour some paint into the top. How much paint can I pour in there? Okay, well, turns out you can pour in pi gallons. Okay, so if I integrate pi times r squared dx, r of x squared from 1 to b, I get 1 minus 1 over b times pi. So as b goes to infinity, the volume enclosed by Gabriel's horn approaches pi. So that Gabriel's horn, the infinite Gabriel's horn, only holds a finite amount of paint, pi gallons, say. But the surface area is infinite. So even if we had all the paint in the world, we couldn't paint the outside of that. So this has been a paradox that people have thought about, as I say, for hundreds of years. The way I resolve it is that when you paint something, you're covering it with a given thickness of paint. Maybe a 100th of a millimeter thick of paint, or maybe a 1/10 of a millimeter thick of paint, okay? Or maybe thousands of molecules thick of paint, right? But if you're going to pour paint into this thing, right, it's going to get stuck eventually. You're pouring it in and it gets so thin that even a single molecule isn't going to be able to make it down any further, okay? So that's how it can be that only a finite amount of paint would fit inside it, but if you wanted to paint the outside of the surface, you need an infinite amount to paint. All right, so as I mentioned before, you too can get this program to look at these pictures and spin them around and stuff like that. It's pretty cool. And especially if you're planning on taking Calc 3, it might be a good idea to get that. So if you search for NAU Mathematica, not Mathematics, Mathematica, it will have a page about how we have a site license for Mathematica at NAU, and you can follow the link that says Getting Mathematica, and you can put it on NAU machines, but you can also put it on your personally owned machine. You can follow that. It takes a little bit of trouble, but I think it's worth it. All right, goodbye.